the opportunity to stay here today. I would like to discuss with you about some anomalies and the way they are related to their potential, and probably the reason why we should consider these anomalies when we test them. So just a few remarks. This presentation is based on a number of works that we have done in the last year. And I would like to thank all the collaborators, in particular, Olga and Alessandro. So what's the point? The point is that in the last few years, very precise measurements of the cosmic migrated ground have achieved 2% precision in measuring most of the topological parameters. And this is, of course, a blessing, but it also represents a challenge, because as our precision increases, then any anomalies or deviations will become statistically significant and eventually point to tension in our current understanding of the universe. And in fact, in the last few years, a few tensions and anomalies have emerged at different statistical levels. Now, for the purpose of this presentation, I would like to classify these anomalies in two different categories. The first one is the category of anomalies between CMB and CMB-independent probes, such as the Hubble tension or the S8 and sigma-8 tension. So they involve typically CMB experiments and experiments beyond CMB, such as local distance flagger measurements for the Hubble tension or weak lensing surveys for S8 and sigma-8. But there is yet probably another categories of anomalies that is the categories that involves anomalies in the values of cosmological parameters as measured by different experiments. And today I would like to focus a little bit on this second type of anomalies and try to study their relation with the Hubble tension, if any. So one notable example of what I call CMB anomaly is the higher lensing amplitude observed in the Planck data at about 2.8 standard deviations. Now, since more lensing is never expected in multiple dark matter, this immediately relates a preference for a closed universe. And in fact, this can also help to explain other anomalies on large scales in the data, and as a result, the kind of Planck indication for a closed universe reaching the 3.5 for standard deviations. Now, excitingly, both the curvature and lensing anomalies may point to new physics beyond the standard model of cosmology, but they may also simply reflect observational systematic errors or statistical calculations of the data, which means that we need to find a way to discriminate possibilities. And I think one effective way to question the nature of anomalies is simply to compare the results from the independence in the experiments. And this can be done thanks to the very precise measurements of the cosmic microwave of the ground released by the Cosmology telescope and the Southern telescope that are probing angular scales actually slightly different. And so if we analyze both ACT and SPT data, we find that they are both in full agreement with a spatially flat universe and with a lensing amplitude consistent with ΛCDM. This may suggest that the Planck lensing and curvature anomalies can simply explain in terms of observational systematics or statistical calculations. However, the same datasets above ACT have shown other mild to moderate deviation from ЛCDM. For instance, from ACT, we have got a preference for a universal spectral index of primordial perturbations in agreement with Harrison-Zeldovich scaling variance spectrum, and in tension with Planck actually at more than 99% of its level. We have got an indication for an effective number of analysis of freedom, which is smaller than expected in the standard model of particle physics at about 2.5 standard deviations. And finally, we have got an indication in favor of early dark energy at about 3 standard deviations. Now, if we look at the Planck data, we find no clear evidence for early dark energy. We are in perfect agreement with the standard model of particle physics for an effective, and we measure the spectral index to be different for one at 8 standard deviations. So again, what makes these CMB anomalies difficult to interpret individually is that different experiments always point in discordant directions. And none of the most important deviations can be cross-validated by independent experiments. This is the reason why actually several precise measurements methods have been introduced to quantify the global consistency in these experiments. And I will refer to this work by William and collaborators, where they introduced this suspiciousness statistic to quantify the global agreement of independence in the experiments by starting from the constraints on the parameter volume of the model. And if we do so, we can actually quantify the tension between active and Planck to be at the Gaussian equivalent level of 2.6 standard deviations. Now, depending on everyone else's level of tolerance, these, I would say, controversial tensions ranging between 2 and 3 standard deviations may be taken more or less seriously. But I would like to argue in this talk that it is actually important to understand the reasons for this difference, above all in relation to some interesting proposed solutions to the agent of tension that call for a new paradigm shift in cosmology while relying almost entirely on the robustness of these observations. So if we want to learn more about the anomalies, we basically have two possibilities. Either we trust the cosmological model and we study limitations in current data, or we trust current data and study limitations in the cosmological model. And I would like to follow both these possibilities. Starting from limitations in the current data. So here we are assuming that ΛCDM is the correct paradigm of our universe. And in this case, the main source of tension between Planck and duct is given by the measurement of the spectral index of primordial perturbations and the baryon energy density. And if we believe that these differences emerge from some limitations in the data, then a logical step is to identify which part or missing part of the dataset is responsible for this discrepancy, and eventually exclude or include them in the analysis. So there are many proposed explanations. One is that this difference is coming from missing data points around the first acoustic peaks in the TT spectrum as measured by Giarè. And you know that in absence of data around the first acoustic peaks, there is a strong degeneracy between the spectral index and omega baryon, as a smaller value of omega baryon can be mimicked by a larger value of the spectral index. And this is the reason why ACT is typically combined with other similar experiments to larger scales, such as W. However, if we now take the Planck data and we remove any data points around the first acoustic peaks, and we just focus on the very same multiple range brought by ACT, what we have got is this. We still measure an S to be different for 1 and 5 standard deviations. We are still in agreement with omega baryon, even though we observe a small shift, but in the opposite direction. So we have got two experiments. We are probably more or less the same number of scales, and we have two different outcomes. So in my opinion, this can cast some doubts that this difference is emerging just from missing data points around the first acoustic peaks. So what about polarization measurements? Maybe the problem is arising from polarization. We have done many tests in this direction, and the one I would like to discuss today is that we have simply neglected any measurements of polarization by ACT, and we have replaced them with measurements by SPT. And if you do so, you basically solve the disagreement of the baryon. We are not in perfect agreement with Planck, but we still have an S peaked around 1. So we can't fully reconcile this difference. Yet another possibility that we have studied is to consider astrophysical data, such as baryon acoustic oscillations, redshift space distortion, or galaxy clustering and cosmic shear observations nonetheless. And if you do so, actually, you just reduce error bars without shifting the general values of parameters, and this actually increases the tension. So from a data point of view, I would say that it's not clear what missing part of the data is responsible for this difference, unless, of course, we assume some observational systematics. However, it is also true that the value of cosmological parameters as measured by the ground depend to some extent to the cosmological model, the global paradigm that we assume. So a possibility we usually study when these anomalies is to extend the cosmological model and check if there is an extended model where this difference can be alleviated or reconciled. So I would like to do now the exercise to consider all the possible simple extensions, minimal extensions to ЛCDM to show that, again, these experiments always go in different directions. We already said that from Planck we have a 2.8 sigma deviations from ΛCDM for the value of a lens, while Act is in perfect agreement with a lensing amplitude consistent with the ΛCDM. We also said that Planck gives a 3.5 standard deviations preference for a closed universe, while Act is in perfect agreement with a flat universe. If we consider the dark energy equation of state, from Planck we obtain a 95% confidence level reference for a quantum equation of state, while Act is in good agreement with the cosmological constant value. If we consider dark matter and neutrinos, Planck is very constraining on the total mass and in perfect agreement with the standard model of effect. On the other hand, Act is less constraining on the total mass, and the goal is in disagreement with the standard model at 2.5 standard deviations for an effective. If we extend the inflationary sector of the theory, we have no evidence from Planck for a running of the spectral index, while Act gives us a 2.5 standard deviation preference for a positive running of the spectral index. So you see that they always go in different directions, and this is the reason why we can't find a model that is able to reconcile this difference, unless when we include the effective number of the distance as a free parameter, in which case the global tension is reduced below the standard deviations, and the reason is that the value of NS now gets back in agreement with Planck. However, in this particular case, we are in tension, if you want, or in disagreement with the standard model of particle physics for the value of an effective. So let me try to just recap and interpret a little bit these results. So at least my personal interpretation is that both Planck and Act show mild to moderate deviations from the ΛCDM. But interestingly, all Planck anomalies are always related to parameters related to the local universe, such as the lensing amplitude, the curvature, and the equation of state of dark energy. And all of these anomalies can be cleaned away if we consider local probes, such as BAO and supernovae, as we shall see in a moment. On the other hand, all anomalies also involve parameters related to the early universe, such as the baryon energy density, the spectral index, its running, and an effector. And they are not cleaned away if we consider local probes, such as BAO or supernovae. So if we not consider the large experimental uncertainties associated with cosmological parameters and we extend the theory, also in extending the parameter spaces, the tension in Planck is mostly caused by a mismatch in the early universe. That being said, let's now try to understand if this may have any implications for the outlet tension. And to do so, I would like to start from a different question, which is how do we measure H0 below the ground? If we look at the same angular Hall spectra, what we can measure is the angular size of the horizon theta from the position of the acoustic peaks in the spectra. If we increase theta, we just keep the position of the peaks. Then we can measure the baryon energy density from the relative amplitude of the peaks, because for instance, we increase omega baryon, we increase the amplitude of the first peak, we decrease the amplitude of the second one, and so on and so forth. And then we can measure the whole dark matter energy density by the absolute amplitude of the acoustic peaks. Once we have measured these three quantities, we can choose a model for the universe. Eventually, we know the sound speed of our photon baryon fluid and everything, and we can eventually go to the sound horizon. Once we know the sound horizon, we know the distance, which is nothing but the sound horizon. And if we now choose a model for the late time evolution, where late time means after elimination, then we can eventually infer the variation. So if now you see that if we assume that the correct value of H0 is the one provided us by the Schuss collaboration, and I want to work with the cosmological model to increase the value of H0 I can get from this indeed, I basically have two possibilities. Either I work at early times and I work on my physics before recombination, or I work at late times and I change the distance from this of the value that I can infer from this indeed. So if we look at this plot, you may say, oh wow, as soon as I include any other background parameter fields, then I have plenty of room to accommodate higher value of H0 in the single data from both Planck and Act. So you may say, wow, these should be the preferred solutions. But it is actually true, because as soon as we consider the measurements of supernovae data, you see that they are not in agreement with these extended backgrounds. And typically, all anomalies at late times are cleaned away, or supernova. But in any case, if your preferred model for the Hubble tension involves new physics and I wouldn't expect actually the disagreement with Planck and that to play any important role, simply because these experiments are mostly in disagreement in the early universe. So let's look a little bit more carefully to new physics, to solutions that involve new physics at early times. Well, in this case, the idea is to change the size of the time horizon to infer different variation. And there are very interesting implications for new physics in this direction. And we cover the energy, which more or less is doing something similar, right? But again, that's fascinating. The idea of these solutions always comes. And one is that we typically find evidence for preference data, but we don't find any clear evidence for energy in Planck data in general for physics at early times. So is it possible that the difference between the experiments is driven partially this preference for new physics in the early universe now? Well, this is a tricky question, and we remain agnostic on that, and we just check what these two experiments are measuring for the early time parameters of interest in this game. So if we consider omega baryon, the spectral index, the sound horizon, the angular size of the horizon, and the distance, you see that both Planck and that are measuring actually things that are not so in agreement, if you want. There is always a shift ranging between 2 standard deviations or even more. Apt in particular allows for greater flexibility in accommodating higher values of the sound horizon than Planck. And Planck, on the other hand, thinks where Apt prefers very small value of H0, which means that if we want to increase the value of H0, we actually have to move towards the region of the parameter space where the tension between the two problems gets more significant. In addition, another important consideration is that the spectral index and the Hubble constant, and actually also in some values, are not positively correlated with pixel ЛCDM cosmology, which means that if we try to increase H0, we also push NS to higher values. And this is typically the reason why these solutions that involve new physics, the universe, typically come with a preference for a unitary spectral index. So let me just conclude and derive some general statements on this presentation. So there is a global tension for disagreement between us and Planck, which can be quantified at the level of 2.6 standard deviations within the ЛCDM model of cosmology. Now, this can reflect observational systematics, new physics, we don't actually know. But I think it's reasonable to conclude that this difference warrants further investigation. Above all, if we want to use this data to study fundamental physics. And here we'll have to provide an example. If we want to use Planck data to study the physics of inflation, they provide very different answers also for well-established inflationary models as Starobinsky inflation. You see that Planck is in perfect agreement with Starobinsky inflation, while this model is basically ruled out by at several standard deviations, simply because you will need too long last epochs of expansion to explain data. So this may also have some implications for the Hubble tension, because we have seen that actual deviations from ΛCDM in the early universe, and its intention with Planck and the early universe. On the other hand, Planck is in agreement with ΛCDM in the early universe. As a result, we have hints for new physics in the early universe, and not clear evidence for new physics in Planck. If instead your preferred model to solve the tension involves new physics at late times, then I would say that as soon as we include local props, you have very little room to accommodate new physics but enough and in Planck. And thank you for your attention.
Are you moving the unknown max to the
Yes, we will. Yes, for us from 600 on, yeah.
No, but I mean, what about the higher one?
No, we are including also the higher multiples, but we are also, there is a clear range of multiples where they overlap, right? Then Planck actually reaches higher multiples. No, we didn't cut that. I mean that we are removing here. We are removing the Planck data around the persists peaks, right?
Right.
So no, we didn't remove the data, but because no, we don't. We didn't remove the
And you,
Okay, can I believe?
you write a new paper.
Yeah.
With these lost in it.
I wouldn't expect actually to change much, right? Because I mean, it's true that here we get higher multiples, but if the idea is that this difference is coming from missing data around the statistics, I don't see this if I remove data around the statistics in Planck.
To what extent is 0.76 overlapping, right?
Yeah.
What a like for like comparison, right?
Yeah. Sure. We can start. It's something we can do in the future.
Questions? Yes, please. We include in your analysis estimates of lensing potential and the lack of lensing.
Lensing, no.
For instance, when it is consistent with coverage of 0.
Do you mean from? Yeah, no, we didn't include lensing. Of course, if you include lensing or any other local props such as VAU and everything, curvature is always consistent with 0. Yes.
But this lensing is part of the same data.
Yeah, but you have some assumptions when you extract the lensing potential. You have some tensions with the lensing amplitude, so we remain conservative. But anyway, the difference between the two probes, it's not changed if you include lensing. That I can tell you because we tested. And if you include probes in lensing in Planck, the difference of an S is still there, and the difference with omega bar is still there. So but yes, it's going if you include lensing, it's consistent with 0, as well as if you include VA, it's consistent with 0. But it's not really the point here because the disagreement between Aft and Planck is not given by curvature, it's given by NS and the current energy density.
The questions.
And have you looked at SPD temperature?
SPD, we didn't check for all the standing models, but in general, it's much more consistent with Planck than Aft.
Then I think it's just polarization.
Oh yeah, I think so. Yeah, and now we have also temperature, so yeah, something else that we can check.